All right, so here's a particular example of a problem that you can apply both Markov's inequality to and Chebychev's inequality to, and one's going to give a better answer. And so let's just look at how it works out. By the way, people watch any of the construction that was going on the Bay Bridge and on the bridge cam or whatnot? Doesn't matter in anybody's lifetime. Interesting. Okay, so we're going to say that on average it takes 45 minutes to cross the Bay Bridge during rush hour with a standard deviation of 15 minutes. And so we're going to imagine some very long list of travel times, how long it took to cross the bridge. And in this very long list of numbers, the average of that list is 45 minutes. The standard deviation of the list is 15. I want to ask, what's the largest fraction of numbers in that list that could be bigger than 2 hours? 2 hours or bigger. Okay. So travel time across the bridge, you never arrive before you leave. So that's a list of non-negative numbers, right? Okay. And Markov's inequality says that the fraction of elements of a list, if the list doesn't have any negative elements, fraction that's bigger than some constant is no bigger than the mean of the list divided by that constant. And the mean of the list is 45 minutes. The constant is 2 hours. 45 minutes over 120 minutes is 37.5%. Okay? So Markov's inequality says, and it's got to be true, that no more than 37.5% of the elements of that list are bigger than 2 hours. Okay. Well, we can also apply Chebychev's inequality to the same problem because we know the mean and we know the standard deviation. So we can figure out what fraction of elements of the list could be really, really big or really, really small. Now, the fraction that are really, really big or really, really small can't be any smaller than the fraction that are really, really big because you're taking the fraction really, really big and you're adding something to it. It can't be negative, right? So if we use Chebychev's inequality, which says can't have too much stuff out there, and say can't have too much out there means can't have too much up there. That makes sense? We've got the inequalities chain. All right, so first we need to figure out what range of values we're talking about. So 2 hours is 120 minutes. How many standard deviations from the mean is that? Well, the standard deviation is 15 minutes. To go from 45 minutes to 2 hours takes 15 minutes, right? It's 15 minutes times 5 is 75 minutes. 75 minutes plus 45 minutes is 2 hours. All right? So this bound, the threshold we're looking for of 2 hours is the mean plus 5 times the standard deviation. So the fraction that are more than 5 standard deviations away from the mean is at least as big as the fraction that's more than 5 standard deviations above the mean. Chebychev's inequality bounds the first thing. The first thing has to bound the second thing. Does that make sense? You're not? Okay. So in fact, it's going to do a little bit better job here because we know that the list can't have any elements that are 5 standard deviations below the mean because 5 standard deviations below the mean is negative 30 minutes. So we know that there aren't any elements of the list that are where it took you less than minus 30 minutes to cross the bridge, right? That doesn't happen. So, all right. So what does Chebychev's inequality tell you? Well, it says the fraction of elements of that list that are less than minus 30 or bigger than 120 is no larger than 1 over 5 squared because that's a range that is beyond, that is 5 standard deviations or more from the mean. 1 over 5 squared is a 25th. That's 4%. That's a much, much, much better bound than 37.5%. They're both true, right? If you can't have more than 4% really big, then it's certainly true that you can't have more than 37.5% really big. But knowing that you can't have 4% is more informative than knowing that you can't have more than 37.5%. So it's sharper. There will be some, yes?
In Markov's inequality, when you say that if your cutoff is 2 hours, then how can you say 2 hours or longer? Like, aren't you computing for that 2 hours and making all of the smaller values as small as they can be so that you can account for those 2 hours?
Okay, so the question is, in Markov's inequality, aren't you sort of assuming that things are exactly 2 hours, and so how can you say 2 hours or more? And why does it work that way? So the inequality does this. What it's bounding is what fraction can be 2 hours or above. And the question is, what makes that as large as possible? And what makes that as large as possible would be if they were all exactly 2 hours. But that doesn't mean that, so what makes the inequality sharp is if the list only had two numbers in it, 0 and 2 hours. Okay, so that's where, if the list were of that sort with only two values, 0 and 2 hours, then you could have exactly 37.5% of the numbers at 2 hours. And at 2 hours is 2 hours and above. Okay? For any other list, if you have more than two values, then the amount that you have above 2 hours is going to be less than 37.5% of the elements. Okay, so it's still an upper bound, but the way that you get what makes it sharp is if the list only has two elements. Otherwise, there's slack. It would be the way it would be said.